So we are going to talk about the universal property of tensor products. I have an earlier video that goes over an explicit construction of the tensor product, so I recommend watching that first so you can get a concrete understanding of what elements of the tensor product look like. In this video, I'm going to use the terminology of vector spaces, but the same reasoning applies to tensor products of modules over a commutative ring. Now, one of the things that makes working with tensor products difficult is it can be hard to define functions on the tensor product. For example, let's say we want to define a function f that goes from the tensor product r tensor r to the real numbers. One way that we could define something on the tensor product is to say f of the sum of a tensor b. So this is some arbitrary element of the tensor product. We're writing it as a sum of pure tensors. This function is equal to the sum of a plus b. So for each of the pure tensors, we add up the real number on the left and the real number on the right, and we just put those all together. If we look at this definition, it seems like it should give us a function on the tensor product. But let's see what happens if we apply f to a specific element of the tensor product. For example, let's say we look at 3 tensor 2 plus 4 tensor 2. This is an element of the tensor product r tensor r. And if we take f of this element here, the definition says that we add up each real number on the sides of the tensor. So 3 plus 2, do the same thing for the second one, 4 plus 2, and we add those up. So in total we get 11. But we know that the elements of the tensor product satisfy a lot of relations between them. For example, if we look at this element, both of them have a tensor 2 on the right side. And one of the properties of the tensor product is that we can combine these two elements. 3 tensor 2 plus 4 tensor 2, this is equal to 3 plus 4 tensor 2. So we can add up these two on the left side. And of course, this is 7 tensor 2. But what is f of 7 tensor 2? Well, by this definition, it should equal 7 plus 2, which is 9, not 11. So these two are the same element of the tensor product. And yet, f is giving us different answers for each one. That's a contradiction. A function can only give us one output for each input. So this thing that looked like a perfectly well-defined function actually isn't a function at all. So this is a big problem. We want to define functions on the tensor product, but because of these relations between elements of the tensor product, it can be hard to tell whether a function is even a function in the first place. The universal property is a solution to this problem. It gives us a way to define functions on the tensor product without having to worry about whether they're well defined. I went over the construction of the tensor product in the previous video, but I'm going to review it here so that I can introduce some notation. To define the tensor product, we first define a vector space Z, which is a vector space with one basis vector for each element, each ordered pair v comma w in the Cartesian product v cross w. So we're defining the tensor product of the vector space v with the vector space w, and we begin by defining a new vector space z. And this vector space has a lot of basis vectors. For every single pair v comma w in the Cartesian product of these two vector spaces, we're going to give this ordered pair its own basis vector in the new vector space. And the way we're going to denote the basis vector of this ordered pair, v comma w, is v star w. So for each pair v comma w, we have an element here, v star w, that is a basis vector for z. So right now, each of these v star w's is a basis vector, which means they're all linearly independent. For example, there is no relation between v star w and v star 2w. You might think that these would be connected in some way, but they are linearly independent. So there's no way to add up some multiple of v star w and some multiple of v star 2w to get 0. There is no relation whatsoever between these two elements in the vector space Z. So right now, when we're looking at the vector space Z, an arbitrary element is going to be some finite sum, let's say sum from I equals 1 to n, of some scalar lambda I times vi star wi. So at each index, we're going to have a pair of elements v and w from the vector spaces, some scalar in front, and this linear combination is an element of z. And each of these linear combinations, if we change the vi, if we change the wi, or if we change the lambda I, each one gives us a new element of the vector space z. Now, to get from z to the tensor product, we're going to introduce relations between these elements of z. And we do that by taking the quotient of z by some subspace. The subspace that we use to take the quotient is this subspace S, which we define as the span of these four vectors. So v star w1 plus w2 minus v star w1 minus v star w2. This is an element of z, and it's an element that we use as part of the span of this subspace S. And we do the same with the remaining three elements here. And this S, we take the span of these vectors for every possible choice of v, w1, w2, and lambda. So any possible vectors and scalars that we can plug into these four expressions, we use all of those to make the span that gives us the subspace S. And then we define the tensor product, v tensor w, as the quotient of z by this subspace S. So in the quotient, v tensor w, each of these elements is equal to 0. Now in the quotient z mod S, we no longer have elements that look like v star w. Instead, in the quotient, they are cosets, v star w plus s. And we introduce some new notation to denote these elements. Instead of writing v star w plus s, we write this coset as v tensor w. So we can write an arbitrary element of this tensor product as a sum from I equals 1 to n of lambda I times vi tensor wi. So this sum right here is the coset of this sum in the quotient z mod s. And taking the quotient of the vector space z by each of these expressions introduces some relations on the tensor product. So each of these equations down here between the elements of the tensor product comes from one of the relations up here. For example, this first line, v star w1 plus w2 minus v star w1 minus v star w2. When we take the quotient by all of these elements, we're essentially setting this expression equal to 0 in the quotient. And so this element on the left, v tensor w1 plus w2, that's the coset of this, is going to be equal to this second part of the expression. Now that we've constructed the tensor product, I want to consider a function that goes into the tensor product. So we're going to define a function tau that goes from the Cartesian product v cross w into the tensor product v tensor w. And we'll define tau by tau of v comma w equals v tensor w. So we'll send each ordered pair to its pure tensor in the tensor product. So this function essentially gives us a way to write the pure tensors in terms of this function tau on v cross w. So let's take a look at the relations that we have over here on the bottom left and see what it looks like if we rewrite this relation by writing each pure tensor as tau of the thing on the left and the thing on the right. So here I've written each of the relations in terms of the function tau. We can see this first expression shows up here, second expression shows up here, and then I've rewritten the third set of equations in terms of these two, the first one here, second one here. Now let's take a look at just these first two equations and see what it tells us about the function tau. Let's look at these equations and consider fixing some vector v that goes in the first argument, and we'll just think about tau as being a function of the second input w. What this first equation tells us is that if we fix v, then tau applied to w1 plus w2 equals tau applied to w1 plus tau applied to w2. And the second equation says that if we fix v, then tau applied to lambda w equals lambda times tau applied to w. Now you might recognize that these two relations on the second input tell us that tau is linear in the second input w. And we can apply the same argument to the second part, where instead of fixing v, we're fixing w and varying v. So tau applied to v1 plus v2 equals tau applied to v1 plus tau applied to v2. Same thing for the second line. So this second set of equations says that tau is linear in v. So the function tau is linear in each of its two arguments independently. And we say that a function that's linear in each of its arguments is bilinear. So this function that sends the ordered pair v comma w to the pure tensor, v tensor w, that's a bilinear map from the Cartesian product into the tensor product. So I've moved our work on the function tau down to the bottom left here to give us more space. And now we're going to move from talking about tau to talking about arbitrary functions on the tensor product. Tau is a bilinear map from the Cartesian product v cross w into the tensor product v tensor w. The universal property of the tensor product tells us that we can write every single bilinear map on v cross w just in terms of this map tau and a function out of the tensor product. So let's start working on that universal property. Suppose that we have a bilinear map f that goes from the Cartesian product v cross w to some other vector space u. The first thing I want to ask is, do we have a way to turn this function f into some other function f hat that instead goes from the tensor product v tensor w to u? Well, let's think about how we could define this function f hat. What would f hat of some pure tensor v tensor w be? Well, it seems like the obvious way for us to define this function would be to say that f hat of v tensor w is just f of v comma w. And this gives us a definition of f hat in terms of f. But we have to be careful before we say something like this, because remember at the beginning of the video, we saw that if you just define some function on the tensor product in terms of the pure tensors, it won't necessarily be well defined. We can have an expression that looks fine to us, but in reality, in practice, it's not giving us a well-defined function. So we need to do more work before we can write something like this down and declare that we're done. It would really be easier for us if we had a way to guarantee that a function on the tensor product is well-defined, instead of having to check it for ourselves every time. Now, the reason that it can be difficult to define functions on the tensor product is that the tensor product is fundamentally a quotient space. And when we're writing a function in terms of the pure tensors here, remember that each of these pure tensors, v tensor w, this is really the representative for a coset. We're picking a specific pure tensor here to serve as the coset representative for v star w plus s. And so when we write a function like this, we need to make sure that it's independent of our choice of coset representative. That's how we can make sure that the function is well defined on the quotient space z mod s. So one way that we can define a function on the tensor product is just to make sure that it gives us the same output for any coset representative of a given coset. And it turns out that there is an easy and rigorous way for us to do that. Instead of starting by defining a function on the tensor product, we instead start with this original space z. So we want to define a function g that goes from z to u. Because z is just an ordinary vector space, it's not a quotient, we're not looking at cosets, we don't have to worry about whether functions on g are well defined. We can just write the definition in terms of these basis vectors v star w, and we're going to get a well-defined function for sure. Once we have a function on z, we somehow want to turn it into a function on the quotient space z mod s. And it turns out that the way we can do that is to check that the function g is 0 on every single element of this subspace S that we use when we're taking the quotient. If that's true, if g restricted to any element of S just gives us 0, then we can define a function, we'll call it f hat from z mod S to u, by just saying f hat of some element x plus s. So this is a coset in z mod s. X is an element of z. We can just define this as g of x. And because g is 0 on the subspace S, this automatically gives us a well-defined function on the quotient. The reason for that is, let's say we look at a different coset representative, some representative other than x. Well, if x plus s is the coset we're considering, then every coset representative is going to look like x plus little s for some little s that's in the subspace. And f hat of x plus s, by definition, that's g of x plus s. But because G is a linear map, that's one of our assumptions that we made when we defined G, this is going to be equal to G of x plus G of s. And we said that G restricted to s is equal to 0. So if that condition is true, then this part is just 0. We can ignore it, and we get just G of x. But that's the same as f hat of x plus s. So this immediately gives us that f hat is the same value on every possible coset representative. Now we have a new objective. Instead of looking at the tensor product at all, what we need to do is start with our function f from v cross w to u and get a function on this vector space z. We need a function, a linear map from z to that same space u that gives us 0 on every single element of the subspace S. So remember that we started out with a bilinear map f from v cross w to some vector space u. And we found out that if we want to get a map on the tensor product, our first objective should be to find a linear map g from the vector space z into u. Now, the basis vectors of the vector space z look like v star w for some pairs v comma w in this Cartesian product. So let's first ask, what should g of v star w be? Well, the most obvious definition here would be that g of v star w is just equal to f of v comma w. So for any basis vector, we take this v and w, we get the ordered pair, and we plug that into f. Now we want to extend this to arbitrary elements of the vector space z. In general, an element isn't going to look like this. This is just a basis vector. So an arbitrary element of z will be some finite linear combination of lambda I times vi star wi. So we want to ask, what is g applied to this? Well, we know g applied to v star w. If we want to extend that to a finite linear combination like this, then there's only one way we can make this extension and still have g be a linear map. In particular, we have to define this as the sum of I equals 1 to n of lambda I times f of v comma w. So essentially what I'm doing here is saying, let's assume that g is a linear map. And if g is linear, then can we use that to figure out g on this entire sum? Well, the first thing we do is, if g is linear, then g of a sum is the same as sum of g of each of these. And then g of lambda I times something, we can take the lambda I to the outside as well. So all we're left with on the inside is g of vi star wi, and that's f of v comma w by this first line. So this is our definition of g for an arbitrary element of the vector space z. And because we defined g by assuming that it's linear, it's pretty straightforward to check that this definition of g here is in fact a linear map from z to w. So you can check each of the conditions for linearity directly if you're interested. So we've accomplished the first part of our objective. We have a linear map from z to w. The next thing we need to get a map on the tensor product is to make sure that g is 0 on every element of this subspace S. So that's our next step. Now remember that our definition of S is as the span of these 4 vectors for every possible v, w, and lambda. So every element of the subspace S is going to look like a finite linear combination, let's say I equals 1 to n, of scalars lambda I times xi, where here I'm using xi to denote any one of these 4 expressions. So this is going to be a sum of lambda 1 x1 plus lambda 2 x2 plus and so on. And each of these x1, x2, x3 is going to be one of these 4 expressions for some value of v, w, and lambda. Now our goal is to prove that g of s is equal to 0 for every possible s. Now, g of s is the same as g of this sum, because these two are equal. So we have g of the sum from I equals 1 to n of lambda I xi. But because g is a linear map, we can split up g of this sum into the sum from I equals 1 to n of lambda I times g of xi. What this is telling us is if g of xi is 0 for every possible xi, then g of s is also going to be 0, because we'll just have a sum of lambda I times 0. Remember that each of these xi's was one of these four expressions. So if we can prove that g is 0 on each of these four expressions, that's enough for us to prove that g is 0 on the entire subspace S. And that gives us our map on the tensor product. So now we want to show that g is 0 when we apply it to each of these four expressions. Let's go ahead and do that, starting with the first expression right here. What is g applied to this? Well, we have the definition of g right here. So let's see how we can turn this into a sum of f of v comma w. The input to the function g is this sum of these scalars lambda I times vi star wi. The first term in the sum here is v star w1 plus w2. So in this case, the scalar lambda in front is just 1. So the term that we're going to get in the sum over here is 1 times f of v comma w. So in this case, the v is just this v here, and the w is w1 plus w2. Next, we look at the second term here. In this case, there is a scalar in front. It's -1. That's our lambda here. So the next term in the sum will be a minus, that's this scalar here, and then f of v comma w1. That's these two. And next, we have the third term. Again, the scalar in front is -1, and we have f of v comma w2. So this is the output for g applied to this first expression. But what is f of v comma w1 plus w2 minus f of v comma w1 minus f of v comma w2? Well, remember that f is a bilinear map. And what that means is that if we fix v, then it's linear in the second input w. So f applied to w1 plus w2 equals f applied to w1 plus f applied to w2. So if we take this first part and subtract the outputs for w1 and w2, because f is bilinear, the answer that we get is 0. And we can apply the same argument to the second expression. In the second case, instead of looking at the linearity in w, we're looking at the linearity in v. But the same reasoning works, and we're going to get 0 at the end. The same deal with the other two expressions. I'll go through this first one. G of lambda v star w minus lambda v star w. So in this case, for this first element, the scalar in front is lambda, and then we have f of v comma w. And then in the second case, the scalar in front is -1 because the lambda is actually inside of the first vector. So here we have f of lambda v comma w. But again, this is just one part of the statement that f is linear in the first input v. So lambda times f applied to v is the same as f applied to lambda v if we fix w. So this is also 0. Similarly, the fourth expression is 0, and therefore the function g is 0 on every single element of the subspace S. So at the end of the day, g is 0 on S because our original function f is bilinear, and each of these expressions is expressing a property of bilinear maps. By our reasoning from before, if we have a linear map g on the original space z that's 0 on S, that gives us a well-defined map f hat on the tensor product v tensor w to u, because v tensor w is that quotient z mod S. And the way that we define f hat on some coset x plus s is just by saying f of x plus s equals g of x, which is well defined because g is 0 on the elements of S. So this gives us the definition of f hat, but let's see what that actually looks like if we write an arbitrary element of a tensor product as the sum of these pure tensors. So what is f hat applied to the sum from I equals 1 to n of lambda I times vi tensor wi. Remember that each of these pure tensors, vi tensor wi, is fundamentally the coset v star w plus s. So what we mean when we write this sum is we're looking for f hat of the sum from I equals 1 to n of lambda I vi star wi plus s. So each of these pure tensors is a coset. When we add them together, the coset that we get in Z is this sum of the basis vectors vi star wi plus s. And now that this is written as just some coset of Z, we can immediately say that this is equal to g of the sum from I equals 1 to n of lambda I times vi star wi. That was how we defined f hat. And now we can use this definition right here, because this is exactly the same as the line at the top here. So this is equal to the sum from I equals 1 to n of lambda I times f of vw. That's just the definition of G. And this gives us the definition of the map f hat. We have some arbitrary finite linear combination of these pure tensors vi tensor wi. If we apply f hat to that sum, what we get is the sum of lambda I times f of vi comma wi. So now we know that this function f hat, defined in terms of f applied to these pure tensors vi and wi, this is a well-defined function on the tensor product. So for any bilinear map on v cross w, this gives us a function on the tensor product, and we know that it's well-defined. We don't have to check anything. Now we can actually get some additional properties of this map f hat. First of all, f hat is linear, because let's take a look at what is f hat of x plus y plus s. By definition, this is g of x plus y. But if we look at what is f hat of x plus s plus f hat of y plus s, this is going to be g of x plus g of y. And we already know from earlier that G is a linear map. So g of x plus y equals g of x plus g of y. And therefore, we've just shown that f hat is also linear. We can make the same argument if we look at f hat of lambda x plus s. So we started out with some bilinear map f from v cross w to u, and we got a linear map f hat from v tensor w to u that's defined in terms of f. I want to ask, is there a mathematical connection? Is there some relation that connects f and f hat? Well, remember, from the beginning of the video, we had this map tau from v cross w to v tensor w that just sends v comma w to the pure tensor v tensor w. This map tau is the connection that bridges f hat to the original function f. Because let's take a look at what is f hat of tau of v comma w. Well, by definition, tau of v comma w is just v tensor w. And then if we look at this definition of f hat here, f hat of v tensor w is by definition just f of v comma w. So f hat of tau applied to vw is equal to just f applied to vw. In other words, f hat composed with tau equals f. This is the mathematical relation between f hat and f. And we can say more than this because, in fact, f hat is the unique map on the tensor product that has this property. Because let's say we have some arbitrary function h, with h composed with tau equals f. Then what is h of v tensor w? Well, we can write v tensor w as tau of v comma w. And because of this relation, this has to be f of v comma w. So this equation determines the value of h on every pure tensor. But we know that the pure tensors generate the tensor product. So because h is linear, specifying h on every pure tensor also specifies h on the entirety of the tensor product, which means that there exists only one map that satisfies h of v tensor w equals f of v comma w. In particular, that map is f hat. So we started with a bilinear map from V cross W to U. And we found a linear map on the tensor product that is the unique linear map satisfying f hat composed with tau equals f, where tau is defined down here. This construction is the universal property of the tensor product. What the universal property says is that for every bilinear map f from V cross W to U, there exists a unique linear map f hat from V tensor W to U such that f hat composed with tau equals f. And we don't just know that f hat exists, we also have an explicit formula for f hat in terms of f, which is given by this equation. So the universal property helps us construct linear maps on the tensor product. We start out by just defining a bilinear map on V cross W, and that gives us a linear map on the tensor product using this formula. And we never have to check whether the map on the tensor product is well defined. We get that for free. So I've rewritten the universal property along with the definition of f hat in terms of f. One of the key properties of this formula for f hat is that f hat of V tensor W equals f of V comma W. And you can also get this from the equation f hat composed with tau equals f. Let's take a look at an example of using this to create a linear map on the tensor product. So let's say I want to define a function f hat on the tensor product r tensor r to the real numbers. And I want this function to be defined by f hat of a tensor b equals a times b. So you can generalize this to f hat of some arbitrary sum of lambda I ai tensor bi, where the definition would then be the sum of lambda I times ai times bi. This is a function on the tensor product, or at least I want it to be, but we have to check whether f hat is well defined. So how do we do that? Well, the answer is we don't start with the tensor product. Instead, we start by looking for a bilinear map and then apply the universal property. So I know in my head that my goal is to get this function as a linear map on the tensor product. But to get this function, I'm not going to start with the tensor product. In order to apply the universal property, I'm first going to consider a map f from r cross r to r. And I want a map here that's going to give me the f hat down here. Now remember, we know with the universal property that f hat of V tensor W equals f of V comma W. So if I want this map f to give me the f hat down here, I need to define f of a comma b to be equal to a times b. So in order to apply the universal property, all that's left is to check whether f is a bilinear map. And you can go ahead and check this yourself, go through each of the properties. It turns out that this multiplication, where we just multiply the two inputs, this is a bilinear map on r cross r. So we have our bilinear map, and the universal property says, therefore, there exists a linear map f hat from r tensor r to r such that f hat composed with tau equals f. And what that means is that if f of a comma b equals a times b, then by this equation, f hat of a tensor b equals a times b. So in fact, this function down here is exactly the function that we get from this f using the universal property. So again, let's review that process. I started out by saying I want a linear map on the tensor product. And I want a linear map that looks like this. But it's hard to prove that an arbitrary map on the tensor product is a well-defined function. So instead, I look at what I want my function to give me and use that to construct a map on r cross r. I take what do I want f hat of a tensor b to equal, and I say this f hat of a tensor b, what I want this to be, I'm going to define that to be f of a comma b. So I use this to define a map on r cross r. And now that I have this map, I don't have to think about the tensor product at all. I just check, is this bilinear? And if this function here is bilinear, then I know for free that this map down here that's defined similarly is both well-defined and linear on the tensor product. Let's look at an example where this doesn't work. Suppose that instead of f hat of a tensor b equals a times b, we use the example from the beginning of the video, which is a plus b. So in this case, the map that we want to define on R cross R is f of a comma b equals a plus b. And in order to use the universal property, we need a plus b to be a bilinear map on R cross R. But you can check this for yourself. A plus b is not a bilinear map on R cross R. So what that means is we cannot apply the universal property, so we cannot guarantee that this function is well defined. And indeed, we found at the beginning of the video, this does not give us a well-defined function on the tensor product. So that's an example of how we can use the universal property. If we want a function on the tensor product, we think about what we want the function to look like, and then we use that to give us a function on the Cartesian product. All we need to do is check whether the Cartesian product function is bilinear, and that will tell us whether this function is well defined. So that's how we use the universal property to get functions on the tensor product.